Lesson 57, projectile motion. We will be able to do kinematics with projectiles. I'm going to quickly talk about this. I'm actually going to compress something that I've taught in my year 10s. I taught this to year 10 engineering maths and it took me a week. I'm going to compress it down into about 10-15 minutes. So yeah, just strap yourselves in. We're actually not going to go as deep as I usually do with them, but that's because you don't need to know it that deeply at the moment. I think maybe when it comes to year 12, you might need to be able to do this, but year 10, year 11, I'm just going to show you the basics. Firstly, what did we do last lesson? Just so we can quickly cover it. Last lesson, we talked about the kinematic laws. We said that the kinematic laws are equations about motion with no forces. There are ways that we can link, now that we've talked about displacement, velocity, and acceleration, there are ways that we can link all of those things together. So for example, a change in velocity is AT, because it's essentially A is a change in velocity over time. So if you neutralize that, you get AT. So if you take your initial velocity, you add on your change in velocity, you get a final velocity. That gives you this equation, V equals U plus AT, which is actually, you can rearrange that to wherever you want. A equals V minus U divided by T, which is the change in velocity over time, which is exactly what acceleration is. We also looked at the second law. We said that, hey, remember that the area under a velocity time graph is equal to the distance. Well, this here is a trapezium, then you know that V plus U times T times a half, because it's how you find the area of a trapezium, will give you displacement. So that gives you the first and second law. The third, fourth, and fifth law can be found by doing various substitutions. I'm pretty sure if you take this, you rearrange, if you take U plus AT, you substitute it into V, then you'll get U plus U, which is 2U, which then that's going to be 2U times a half is U times T, so that's how you would get the UT. Then you would have a half A times T squared, because so that's how you substitute this into here to get this. You rearrange and substitute to get this, to get the fourth one, and I have no idea how you get the last one. I could figure it out maybe you take these new ones that you just made, but I don't know. Somehow you can get this last one. Each of these kinematic laws is missing a term, and so that's important to recognize. And once we did that, we did 4 examples. The first example we did was just a straight up substituted in, done, bish, bash, bosh, 1 mark. Second one we did was, all right, well, we just got to substitute in, but we've got to rearrange it. That's fine. Third one we did was, not only do we need to rearrange, but we've got to be really careful about directions and what's going on here, and which direction we say is positive and negative and so on. And the last one was a hard one, which was actually a combination one, but it was just sort of designed as a bit of a challenge. Now I set you guys to work on 9.4, but as you guys were working on 9.4, I had a quick look at the questions and I discovered you kind of need to have a little bit of an idea of what projectile motion is for some of these questions. Now it's a bit weird. The other book, the Heinemann book, actually spends a whole chapter looking at projectile motion. Whereas this book that we use, the Jacaranda, it just sort of assumes that you know what projectile motion is and, you know, deal with it. So it's a bit like, okay, well, because I think you guys need to know what it is, let's spend a little bit of time talking about it. I know I'm talking very quickly, so if you need me to slow down, please say so in chat. Projectile motion. What is projectile motion? First things first, projectile motion is the motion of an object through the air in 2 dimensions. Okay. Now we're usually for this topic we're just going to consider 1 dimension, but just so you're aware, it is through 2 dimensions, but it's specifically through the air. The motion, there is something missing here that I wanted to talk to you guys about, but I will. I might add that here. Sorry guys. So yeah, I will read this out while I'm doing it. So the idea is there are two types of velocity. They are horizontal and then there is vertical velocity. The difference between them is horizontal velocity is just how much you threw something to the right or to the left or whatever. It's actually completely independent of gravity. Okay, it doesn't matter how much gravity you've got. Where the hell is the stupid what color? Oh, there it is. It's actually completely independent. There. Back to the actual slideshow. It's actually completely independent of how much it was thrown to the up or down. The vertical velocity is dependent on the initial velocity, so it's dependent how high you threw it, but it's also dependent on gravity, which accelerates at 9.8 meters per second squared. That is the acceleration of gravity. If it doesn't say in a question, then that's what you would assume it is. So you can have like, here's three different situations. The first one is I'm dropping a ball off a cliff or a ledge or a building, and it has initial velocity of 0, and then it just speeds up as it falls down towards the ground. Nice and easy to do those ones. This one is where it starts to become challenging, when you throw an object up and then it comes back down. That is a that velocity is you can see that the initial velocity is going up and then it gets slowed down until here the velocity upwards is 0. It's actually not going up anymore. And then it starts traveling down. This one is again the same as this example to the left, except you've also thrown it to the right. So it goes up and it slows down its upward ascent, and then it starts coming down. It starts coming down at a faster and faster rate. Now, the reason why we spend a little bit of time at the start breaking down vectors and breaking into different components using the sine and cos is for this exact purpose, so that we can break them up into vertical and horizontal components. I just thought I would throw that out there so you guys can see, hey, guess what? This is why we spent about a week talking about vectors. Let's keep going. So if we look at, oh my God, okay, ignore this, whatever, bouncing, whatever. Here we go. So this is a cannonball getting launched off. Its vertical velocity initially is 0. Then it gets faster and faster and faster and faster downwards. Whereas its horizontal velocity is the same all the way across. Its horizontal velocity doesn't change. Cool. Let's jump into the next one. This is just another example. I'm going to put these slides are on the classroom, so if I'm going through them too quickly, don't worry, you can check them out later. Okay, so this is actually throwing it off a cliff. This is one of the harder ones that I didn't actually explore in year 10, but I'm going to expect you guys to be able to handle. It initially travels upwards, and you can see that its vertical velocity is initially positive. Watch Vy. Initially, it travels upwards, but it slows down until eventually it reaches 0. And then it starts falling towards the Earth, and its Vy increases higher and higher and faster and faster and faster. Whereas Vx, the displacement to the right, is the same. It is always traveling at 60 meters per second to the right. Doesn't matter what. So these are the basics of projectile motion. So far, all I've said with projectile motion is that objects, the horizontal and vertical velocities are separate. Now, what formula do we tend to use with projectile motion? The formula we tend to use with projectile motion is usually this one here. S equals ut plus half at squared. The vertical displacement, so the vertical velocity, the vertical displacement S is based off this formula. And this formula is the initial speed going upwards, and then it's going to be, whereas this one is going to be negative 9.8 because you're slowing down, right? And so therefore, the distance that you cover is going to be given by this. How long was that in the air for? These kinds of motions here. The motion is parabolic we could trace this as a parabola. If I was looking at my displacement, as time goes on, initially I'm going to be going up, but then as time goes on, my displacement's going to come back down again. I'm going to reach 0. If you substitute 0 in here, you will get two solutions, one here and one here. So that will, and those solutions will be for t, which you can use to figure out, well, how long did it take to get back to the ground? And that's going to be a useful idea that we will talk about. And I'm going to show you later on the exact question that made me want to teach you guys projectile motion. But yeah, again, we're going to use most of the time this one. And how I actually do the projectile motion questions and how a lot of other teachers teach it is that I usually teach it like this. I break up the motion into two parts. The first part, which is the ascent, is going up. How long does it take to go from the ground up to this point where it stops moving upwards? How far did it go in that time? And then I have a second area, which is the descent, you know? How long does it take to go from the top to it hits the ground? Those two things are really important for us to sort of understand to begin to talk about projectile motion. All right, so let's do a question so that we can get a little bit more confidence in this stuff. This question here is actually pretty, I've got two questions. I'm probably going to skip this question here, but I will talk about it briefly. And then I want to show you guys the question in the book that made me come up with this question. And then I'll show you basically how to do it, but I won't go through it completely. All right, so I've been talking for half an hour. Crap. All right, here we go. I want you to jot this down if you could. And I'm going to, because I'm about to launch, I'm about to put it onto the document camera and then we'll go through it together. So a rock is thrown upwards off a cliff. The cliff is 100 meters tall. The rock travels 15 meters up before it starts to travel downwards. How long was the rock in the air? That's the question here. No, someone's asked, do I have to factor in terminal velocity? We do not have to factor in terminal velocity. That we can't really calculate that. Anyway, we will usually assume that it's just falling naturally. Here we go. Let's do this. I'm going to cast this to my I'm going to cast my phone so you guys can see the whoopsies, and I've taken two photos by mistake. Again, the problem here is you guys can now not see the question. So you guys are going to have to just either have it open or hopefully you've written it down, but you guys might have to jot it in here. So the thing I would do straight away in a question like this, and what I would always suggest you guys to do, is to draw a picture. Yes, it's just like maths. It's always drawing a picture first. So we've got a cliff. We've got someone standing on that cliff with a rock, throws the rock up, and then the rock falls down off the cliff and then it hits the ground eventually. All right, cool. What information do we know? We know this cliff is 100 meters tall. That says 10. 100 meters tall. And we know that it traveled upwards 15 meters. So here we go. Here's 15 meters before it started to fall downwards. So this person lobbed it up and then it started to fall down. The question is, how long was it in the air? So I'm going to break this down into two parts. I'm going to talk about the ascent and the descent. So going upwards and then going downwards. Let's talk about going upwards first. Okay. Now we know that it's traveling. We know that it's traveling 15 meters because it went 15 meters up. Okay. We know that acceleration is negative 9.8. Now I say negative because I'm going to assume that up is positive. Okay. So therefore our displacement is going to be upwards because we're going against gravity. We don't know what our initial velocity. We don't know how fast it threw it upwards, but we do know the final velocity. The final velocity is 0 because once it reaches the 16-meter mark, it doesn't keep going up. At the 15-meter mark, it doesn't keep going up. It stops going up. So that's how we have this final velocity here as 0. And that means we've got SAV. We want to know what T is. We've got to find an equation that has these factors in it. Does anyone want to say in chat what the equation is? It's got SA, V, and T in it. Which one should I use? Put it in chat or say it out loud if you want. What is the formula that I should use that's got S, A, V, and T in it?
S equal VT minus 1/2 AT squared.
Thank you very much. S equals VT minus half AT squared. Right, cool. Now we know, I'm just going to simplify this before I rearrange this. If I know V is 0, then I can cancel this out because 0 times T. So that just gives me S equals negative half AT squared. Great, cool. So that means if I've got S divided by negative a half, negative a half A, that will give me T squared. T squared is going to be S divided by negative a half times negative 9.8. That's how we cancel out the negatives. T squared, I'm not sure if you guys can see, I'm writing right now right down the bottom. T squared is going to be, substituting it in, 15 divided by 0.5 times 9.8, 3.06. T equals 1.75. Beautiful. Okay, so that's the first part. Now the second part I'm actually going to do over here. That's why I went downwards so much. So the second part is this part here. Now for this part we know that our S, what displacement does this thing fall? How far does it fall? Someone in chat, anyone? How far does it fall? How far is this distance here? Come on, guys, out loud.
115.
115. Thank you. Negative 115. Straight away, someone's probably thinking, whoa, 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 why is this one negative? The reason why this one is negative is because it's going downwards. It's actually falling downwards rather than a going up against it. It's going down. The sign here is important, but if I've made a mistake, it's more important that I understand what the final sign should be. So time should be positive. If I get a weird answer and time is negative, then I know that there's probably going to be a mistake made in my signs. I might have this wrong. I'm going to be completely honest with you. I might have this wrong, but I'm going to see if I can figure it out anyway. Now this time, the final velocity isn't 0. The initial velocity is 0. Because remember, we're not moving up or down at all at this point. So our initial velocity is 0. U equals 0. We want to work out T. So what's got S, A, U, and T in it? Oi, shush. Anyone know? What's got S, A, U, and T in it? You can put, yep. Quickly, S equals UT plus half AT squared. Thank you, you're right. S equals UT plus half AT squared. Again, because U is 0, that's going to cancel this out. So S equals a half AT squared. Now, that means that, again, T squared equals S divided by a half A, which is going to be, that means that this is negative 115 meters. We're going to divide by a half times negative 9.8, which is going to give me, well, so we've got negative, I'm not sure, you guys can't, for some reason you guys can't see. Is this lagging? Can you guys see what I'm doing? What's going on here? I think it's lagging. Why is the acceleration negative? Okay, so while I'm trying to figure out what's going on with my poor little someone asks, why is the someone's asked, why is the acceleration negative? Again, we've said at the very, very start that up is positive. So that's why the acceleration is always negative. It's always going downwards. Whereas this one, the displacement was up, whereas now the displacement is down because the object has moved downwards. So that's why. Now, if I end up, and you can see how it works here, I'm going to end up with negative 115. I'll put this into my calculator. Negative 115 divided by negative 0.5 times negative 9.8. Negative divided by negative is going to give me a positive, which gives me 23.4, but that's still t squared, so therefore t equals, if I square root that, 4.84. So therefore t total, the total time that's spent in the air, is going to be 4.84 plus 1.75. Someone should be yelling at me because I've rounded these answers off, but it doesn't matter well, I don't think it matters too much, especially if it's my question. The answer is 6.59 seconds. That's how long it's in the air for. Now, I chose this question particularly, I made this question here with the cliff, particularly because it was designed to be difficult. And this is one of the ones that I would not normally give to a Year 10 student. The reason I wouldn't give it to a Year 10 student is because usually I get them to cheat. What I do is normally I tell them, hey, if you throw, like, what I'll give them is these types of questions, but I'll just do something like this. So once I figured out the time for the first half, they just multiply it by 2 to get to the time for the second half. And that works a lot, but it only works if you land at the same point. So if you're not landing at the same point, for example, in this situation, you're going to have to split these two things up. Okay?